And I would like to build up from here. We observed that if we have a point charge Q and we surround this by a sphere which is a closed surface, this sphere is the outer boundary of a volume, then the total flux that pierces through this closed surface, which is just the integral of the electric field over the entire area of this closed surface. Remember, this is a closed surface. So some authors or some books would also like to put in a circle here to denote a closed surface. Okay, but I may or may not put a circle, so it's a matter of choice. So this flux is given by Q over epsilon naught. And later we notice that it's not important that this outer surface is a sphere. This outer surface could be an arbitrary shape which encloses this charge. Now what do I mean by enclose? Enclose really means that this surface bounds a volume. It's on the outer periphery of a volume and there's a charge inside the volume. So this is what the meaning of enclosure is. So if this closed surface encloses a charge Q, then the total flux through that surface is Q over epsilon naught. And this surface could be arbitrarily shaped. Therefore, this also means that I could have this charge inside this surface anywhere. I could have this charge here. Still the flux through this surface is going to be Q over epsilon naught. I could have the charge somewhere else. This charge would even be here. So if I draw a surface like this, and this charge is enclosed by the surface, then the flux through this surface is also Q over epsilon naught. So this means that the charge could be anywhere inside the surface. Alright? And the surface could be arbitrarily skewed. It could have any shape whatsoever. The only requirement is that it must be a closed surface. Okay, it must not be an open surface. This also means that if I have a surface like this and I place a charge Q1 here and I place a charge Q2 here and I place a charge Q3 anywhere inside the surface, and likewise I have a large number of charges Qn, then I can compute the flux due to each of these charges separately because of superposition. Each one of these charges will produce a flux, and the total flux that pierces this arbitrarily shaped surface will still be given by Qi over epsilon naught summed over all the Q's. This is going to be the total flux through this surface. And remember, flux is a scalar quantity, so you can add scalars per your will. There's no damage done because it's not a vector, and you don't have to respect the direction. The flux is just a scalar. It's a dot product between two vectors, which turns out to be a scalar. Alright. Another possibility is that you don't have discrete charges, rather you have a charged volume, a charged mass. For example, this object here, this is not a point charge, of course, so if you put charge on this object, it's going to be a charged volume. So I could have a distribution of charges. So now this macroscopic body is not a point charge, it's a collection of point charges that form a continuum. And the total charge on this macroscopic object is Q. And I would like to draw a surface around this macroscopic object. The flux through this closed surface is going to be capital Q over epsilon naught. If I draw another surface, for example, this surface, which only encloses a portion of the macroscopic volume, and this is the portion that's enclosed, shown in yellow. And if this charge that's enclosed is Q dash, then the flux through this surface is going to be Q dash over epsilon naught. G. So the last part is that I draw an arbitrary surface that encloses only a portion of the charge. The portion of the charge that's enclosed is Q dash. So by Gauss's law, the flux that pierces through this surface is Q dash over epsilon naught. Likewise, let's consider the following scenario. I have a charge, say it's a point charge Q, and my surface looks like this. It's a pear shape, and this charge is right at the edge of the surface. By Gauss's law, the flux through this surface is going to be Q over epsilon naught. Now, if I just make this constriction smaller and smaller, my surface now stretches off like this. It still encloses the charge. Again, the flux through this surface is going to be Q over epsilon naught. However, if I pinch this surface a little bit so that I snap over the charge, and now my surface of consideration, the Gaussian surface, is outside the charge. Now what's the charge enclosed? Inside this sphere, inside this surface, it's zero. So the flux through this surface is zero, even though it's present in the vicinity of a charge. So by Gauss's law, the flux through this surface has to be zero, because it doesn't enclose any charge. But flux zero doesn't really mean that the electric field is zero here, is zero here. The electric field could be anything. So if you draw the electric field lines due to this point charge, of course they're going to be pointing radially outwards. So you will quickly observe that any field line that's entering this volume and piercing the surface once has to leave this volume. It has to pierce out of the surface. So in one of these cases, the flux is positive, and in the other case, it's negative, because the area is always pointing normally outwards. So whatever flux line enters this volume, it has to come out, it has to go out. So the flux contributions due to incoming lines and due to outgoing lines, that's going to be equal and opposite. For example, if I have a sphere and I have a charge plus, or let's talk about it, my negative charge. I have a charge minus Q, and if I draw the field lines due to this charge distribution, there's a field line that enters the surface here and leaves the surface here. Now just consider this field line, and if I were to draw unit normals to the surface, the unit normal here would point in this direction. This is the unit normal dA at this point, and the unit normal at this point is dA2, and it points in the left direction. It's normal to the surface because by convention we're taking the area vectors to be pointing normally outwards. So here the electric field and the area vector are 180 degrees apart. Here they are parallel. So this would give a cosine theta which is negative, this would give a cosine theta that's positive, and the contributions would be equal. So the flux due to this corresponding to this electric field line will cancel out. So the total flux through this surface is going to be zero because it does not enclose any charge. Now what good is Gauss's law for? How does it help us in solving problems? Gauss's law always gives you the flux through a surface. It always works. There are no conditions in which Gauss's law has been found to be invalid. If Coulomb's law is correct as an inverse square law, then so should Gauss's law be correct. And there's a question in Friday's recitation that addresses this point. What if the Coulomb law were not an inverse square law? What if it were an inverse cube law? Right, you have to find that out. You have to find that out. Then Gauss's law will not be valid anymore. Okay, with this basic background, which forms one of 4 Maxwell's equations. This is Gauss's law, and we've quickly jumped onto one of Maxwell's equations early on in this course, but this is good. So now let's look at a few implications of Gauss's law. Yes? They don't cancel out each other. The total flux to this surface comes out to be 0. Because some field lines will have a positive contribution to the flux, others will have a negative contribution. No, it's also possible for this. We've already shown by construction in the previous lecture that flux to any surface equals the charge enclosed. And whatever that surface is. So if there's no charge enclosed, the flux has to be 0. So you can draw any surface you like. Draw an oval shaped surface. You'll still get 0 if it doesn't enclose a charge. Okay? So if I have a charge and my surface is a closed surface in the shape of a boomerang, like this. Now this surface is also a closed surface. It doesn't enclose any charge. There is no charge inside the volume which is bound by which this surface bounds. So the flux through this surface is going to be 0. Okay? So this, you have to come to grips with this psychological impression that the flux to this surface, which is a closed surface, is 0 because it doesn't bound any charge whatsoever. Now let's consider once again a point charge. Now what I would like to do, I would like to talk about the role of symmetry. Where does Gauss's law help in solving certain problems? What's the utility of Gauss's law? Gauss's law is in fact quite universal in its implications. It has a huge variety of applications. Now consider a point charge once again. Now if I were to draw a sphere around this point charge, and of course I'm drawing a cross section of the sphere. The sphere is 2-dimensional, it's a closed surface, and this point charge is at its center. Now what I do know is that the flux through this surface is going to be, this is Q, the flux is going to be Q over epsilon naught by Gauss's law. And I've also derived this from Coulomb's principle, because the electric field magnitude is going to be the same. This sphere is at a radius r. All points of the sphere are equidistant from the charge. And the normal vector is always parallel to the electric field. So we've derived this from Coulomb's law. But now we can forget about Coulomb's law for a minute and use Gauss's law as our starting point. So this is the flux through this surface. Now suppose I'm given Gauss's law. I start off with Gauss's law. And I would like to find out the electric field at the surface. Okay? So I know by inspection that the electric field has to point radially outward. And the magnitude of these electric fields at all points is the same, even though the direction is different. But the direction is always along the radius. It's normal to the surface, so it's always along the radius. Remember that this is a sphere, so there are electric fields coming out as well. I'm only drawing a cross section. And at each point, the area vector is not parallel to the electric field, it's normal to the surface. So at each point you have a pair of electric field and the unit normal. And both of them are parallel. So if I were to form the dot product, it's just going to be the magnitude of E multiplied by the small area patch that we're talking about, which is dA. And then I integrate over the entire surface. This should give me the charge enclosed over epsilon naught. So this is my starting point. I started off from Gauss's law by considering the symmetry of the situation. So I consider the geometry of this problem and I find out what direction the electric field is going to lie in, what is its magnitude, and I state the Gauss's law. This is just Gauss's law. Now from Gauss's law I would like to determine the electric field. So I can do that. Please no talking in the class. You sit together and you always talk. That's not allowed. So this is the starting point. Now I know that the electric field, now this is the magnitude, and it's constant along this radius, it's constant. So I can pull this out of the integral. That's easy to do. So I have E dA. This is just the area of the surface of the sphere, which is 4 pi r squared. E 4 pi r squared. This equals the charge enclosed Q over epsilon naught. This means that the electric field at a distance r equals Q over 4 pi epsilon naught r squared. Nice. So this was our Coulomb's law. So we can start from Gauss's law, consider the symmetry of the situation and use Gauss's law to our advantage and find out the electric field starting from Gauss's law. Gauss's law is always valid. Now suppose I have the same point charge Q, and instead of a nice sphere, what I do have is a cube, and this charge is placed at the center of the cube. So now this charge is exactly at the centroid of this cube, at the center of gravity of the cube. So this cube is just a hypothetical surface. All of these surfaces that I am drawing, they can be hypothetical surfaces. They need not correspond to anything physical. They may or may not. Now if I consider this cube, is Gauss's law valid? Gauss's law is always valid. There's nothing stopping you from validating Gauss's law. Gauss's law is always valid. The flux through this closed surface is again given by Q over epsilon naught. And you always have this equals the flux, which is E vector dotted with dA. This is the flux through the surface, and this is always valid. But the point is that for this Gaussian surface, here on the top surface, the area vectors for the small patches that you would like to make are always pointing upwards. However, if you were to draw the electric field on this surface, right above the charge it will point upward, but as you move away from the center, it's going to point radially outward. It just points radially outwards at some angle. So the relative angle between the electric field and the unit normal, the patch areas, is changing along this surface. So it's not easy to calculate this dot product locally, because this dot product is going to be different at different points on this flat surface. Because you've drawn a flat surface, a cubical surface, like the paintings Picasso draws. It's cubism here. But the charge is a point charge and the electric field is spherically distributed. It's radially outward. So you haven't been able to draw a surface, a Gaussian surface, that reflects the symmetry of the electric field. So even though Gauss's law is valid, you do not have the luxury of bringing this electric field out of the integral and simplifying the expression to find out the electric field. So even though Gauss's law is valid, the choice of the Gaussian surface is poor. It does not reflect the symmetry of the electric field. So what you would like to do is you would like to draw a spherical surface. Another point of consideration is that if you have a charge, but you draw a spherical surface, but your sphere is not concentric with the point charge. Once again, even though you do reflect the symmetry of the electric field at this point is going to be larger than the electric field at this point, because this point is closer to the charge. Therefore, you cannot pull out the electric field from the integral. It no longer is a constant over this surface. So even though Gauss's law is still valid and the flux through this surface is still given by Q over epsilon naught, you cannot use Gauss's law to your advantage, because the choice of the Gaussian surface is poor. Okay, so Gauss's law is always valid, and in many cases, if you think carefully enough, you can use Gauss's law to your advantage. Now let's look at a few applications of Gauss's law. Suppose I have a line, and this is a one-dimensional line and it's charged. Okay? So this charge that is uniformly distributed on this line, and it has a linear charge density lambda, which means that per unit length the charge is lambda, and suppose it's positively charged. Okay, now what we would like to do, I've taken a point P that is at a distance, a normal distance r from this line charge, and I would like to find out the electric field due to this line of charge at point P. Now if I were to use Coulomb's law, what I would do, I would take a patch here, find the charge on this patch, find this distance and use Coulomb's law, and this will give me an electric field. We'll have two components, so I will sum up or integrate over the entire length of the charge, but this is really cumbersome to do because one, this line extends to infinity and the calculation turns out to be quite hefty. In tomorrow's recitation there is a problem in which we will solve this from Coulomb's law. Right now I am going to expound to you the power of Gauss's law. How can Gauss's law come to our rescue in order to determine what the electric field at point P is? So first of all, we have to use our common sense and knowledge of electromagnetism to find out what direction would the electric field point in. Alright? Now, can you guess, make a rough, intelligent guess, what direction would the electric field point in? Ji aap. Towards point P. So you're at point P, you want to find the direction of electric field. What direction is it? Up, down, left, right, outwards? Ji? P पे हाँ, P पे टेस्ट चार्ज रखेंगे, फोर्स किस डायरेक्शन में एक्ट होगी इसमें? Outward, outward मतलब ब्लैक बोर्ड से बाहर? Towards the line. So if I put a positive charge here, a test charge, will it experience a force towards the line? Upwards. Alright? So the field here will be normal to this line, right? And it's going to point away from the line because it's a positive charge. Now, why cannot the field point in any other direction? Why is this the only field that's possible? Suppose, hypothetically, that the field would point in this direction, right? It could point in an arbitrary direction. Now this electric field could be resolved into two components. Any field can be resolved into its components. So this field could be resolved into a yellow component and a blue component. This yellow component is normal to the line and this blue component is parallel to the line. Now, my argument is that a component parallel to the line cannot exist. Why? Because it's an infinite line of charge. What's so special about being here and having an electric field that points from one point to another? It really doesn't. Why can't the electric field point in this direction? What's so special about the right direction? Nothing. You stand here, you look towards the left, it's an infinite line of charge. You look towards the right, it's an infinite line of charge. So there's nothing special with this direction, as there is nothing special with this direction. So there is nothing unique about these directions. It's an infinite line of charge. Hence, these components cannot exist. They don't make sense. The only component that does make sense is this yellow component that is pointing away from the field, from the line of charge. Okay? So, at a distance P, at a point P, I'm drawing this P again. I can take this P anywhere because it's an infinite line of charge. the electric field is going to point normal to this line and in an opposite direction. Let me draw this line of charge again in a more straight fashion so that you're not confused. So I'm just drawing a section of this line. This is point P. The electric field is pointing in the upward direction here. This is something we know by symmetry, by the symmetry of the problem. It cannot point in any other direction, because if it does, it will have a component parallel to the line. It does not make sense because it's an infinite line of charge. Now, if this is the direction of the electric field and we would like to use Gauss's law to our advantage, we would like to draw a surface, some Gaussian surface that surrounds this line of charge. We notice that if we draw a line that is parallel to this line of charge, then all the points on this line are going to be equidistant from the line of charge, and the direction of the electric field on all of these points is going to be the same because they are equidistant from the line of charge and they're all going to point in the upward direction. So what I would like to do now, I would like to draw a closed surface. So the closed surface that I can think of is a cylinder here. Okay, if I draw a cylinder such that this is the length of the cylinder, so if I drew this Gaussian surface such that the line passes through the axis of the cylinder, then there is a curved surface and there are two end caps, two poles. This is what Gaussian surface I would like to propose. Now what happens here is that on the curved surface, all points on the curved surface are equidistant from this line of charge. Now if I view this line of charge from here, what would I observe? I'm observing a line of charge that's coming towards me, it's positively charged, and I've drawn a cylinder. The cylinder is coaxial with this line of charge. This is what I will observe if I view the cylinder from here. And here, the electric field is always pointing radially outward. So the electric field here is pointing upward, here it's going to point downwards. Here it's going to point out of the plane of the paper. It's always pointing radially outward. So the electric field points like this if I observe it from a cross section, and that's alright. Because if I were to draw small patches on this surface, the unit normal at each of these points is also parallel to the electric field. So the unit normal is always parallel to the electric field. So I can easily form a local dot product. Okay, so I've drawn a Gaussian cylinder which is coaxial with the line of charge. Now I can use Gauss's law. Gauss's law simply states that the flux through this Gaussian surface, the hypothetical surface that I've drawn is E dot dA. Now this is a local dot product. I will compute this dot product on all points of the surface. Now the surface has three components. It has a curved surface, it has a right cap and a left cap. Okay, so if I use a curved surface, on each point of the curved surface, the electric field and the unit normal are parallel. So the angle between these local vectors is 0. So I can write E dA cosine of 0, which is 1. This is on the curved surface, plus some E dotted with dA. I have not yet opened up the dot product because I am not sure about the directions here. On the right cap, right end, plus E dotted with dA on the left end. Now if I take this surface for example, the area vector is always pointing parallel to the wire and normal to the electric field. So if I form the electric field here, if I find electric field here, it's normal to the area vector. Here it's normal to the area vector. At all of these points it's normal. So this turns out to be 0. Because each of the local dot products is 0. Likewise, this turns out to be 0. Now why can I take the electric field here outside the integral? Because the electric field has the same magnitude on the curved surface. Because all points on the curved surface are equidistant from the line of charge. And it's an infinite line of charge. Okay, so I can take this thing out. This is the electric field at the point P. And it's the electric field at all points on this curved surface. All points that are at a distance r from the line of charge. So I can take this electric field outside the integral. I will get E at the point P, any point P that's at a distance r from the line of charge. Now what's the total area of the curved surface? Two pi r into the length of this cylinder that I've drawn by myself. The cylinder does not exist in reality. I've just drawn it out of my imagination. It has a length L. So I get 2 pi r L. But this is confusing because if I draw a bigger surface, a longer surface, L will be larger. So I do not want a result that depends upon my imagination. So this is the left hand side of Gauss's law. This must equal the charge enclosed by this Gaussian cylinder. And what's the charge enclosed? What's the charge enclosed? The charge per unit length is lambda. Lambda over L, lambda times L. So this is lambda times L, which is the charge enclosed. I divide this by epsilon naught, the L goes away. So the answer does not really depend upon my imagination. The electric field at point P, which is at a distance r from the line of charge, is simply given by lambda over 2 pi epsilon naught r. It has an inverse dependence. Not an inverse square dependence, not an inverse cube dependence, rather an inverse dependence. So if this were a point charge, and if this were the radial distance from the point charge, for a point charge the field drops off quadratically, but for a line charge it drops off less steeply, it drops off gently as 1 over r, like a hyperbola. This is a parabola. Okay, so now we've used Gauss's law to our advantage, and we've actually found out the electric field at some distance from an infinite line of charge. Alright, now there was a question here somewhere. Yes? This part? So we know that we have to use this expression for Gauss's law, E dot dA, this equals the charge enclosed over epsilon naught. So do you understand this? Now this has to be equal to charge enclosed Q over epsilon naught. Now charge is distributed on this surface with a density lambda. This is the charge per unit length. So if I would like to find out the total charge inside the volume that is bounded by the Gaussian surface, that's going to be lambda times the length of this, which is L. So lambda L divided by epsilon naught. Yes?
So if the cylinder was hollow, in that case would D remain same or would it change?
Good question. The question that the gentleman has asked, what if this cylinder is hollow? Well, the cylinder is hollow. This is just a surface. We're drawing surfaces, we're not drawing volumes. This is the outer surface of a cylinder. Of course that's hollow. It's a surface, okay? And the Gaussian, in the application of Gauss's law, you deal with surfaces. So it's a surface, not a volume, it's hollow anyway. The electric field does not depend upon what kind of Gaussian surface we choose. It's independent of that, it's physical reality that we're dealing with. That does not depend upon what kind of Gaussian surface we choose. Okay, so the electric field just exists. And we are using Gauss's law to our advantage to find out what the electric field is. Okay, solving the same problem using Coulomb's law may be an exercise in vectorial acrobatics. Gauss's law helps us. Let's look at another example. Quite an interesting example. So this was a line of charge, an infinite line of charge. So I have 20 minutes before I can show you some stuff. So now what I would like to do or discuss is an infinite sheet of charge. Now suppose this line was one-dimensional. Now suppose I have a sheet which is two-dimensional and it's infinite in size. It's a flat land. It's a big flat sheet which is very large. So I can draw the sheet here. Let's draw the sheet here. And of course I'm a finite being, like all of you. So I cannot draw an infinite sheet, I will just draw a section of this infinite sheet. Suppose it's positively charged. And this charge is uniformly distributed on the surface. It's a surface anyway. And now I would like to talk about charge per unit area. So this is an areal charge density, which I denote by sigma. Okay, the charge coulombs per meter squares are the units for this areal density. That's a linear density. This is an areal density. Now I pick up a point P. That is at some distance r from the infinite sheet of charge, and I would like to find out the electric field at point P. Coulomb's law would be a nightmare here, because now you would like to break this up into small areas and find the electric field due to each of these areas and then integrate from minus infinity to plus infinity, and it's a two-dimensional integral, so it's going to be cumbersome. Let's use Gauss's law to our advantage. For that great German mind in the 19th century has given us this law. Why not use it? So we would like to find out the electric field at point P. Now we notice that if I draw a plane that's parallel to this plane and it's at the same distance r from this plane, so I draw another plane that pierces P and it's at the same distance, it's parallel to this plane, in other words, the electric field at all of those points is going to be the same, because this is an infinite sheet of charge anyway. And could you please tell me what direction the electric field is going to point in? At this point P, it's going to point in this direction, in the right direction. Okay? So what I would like to do now, I would like to draw a Gaussian surface that actually matches the symmetry of the problem. So the electric field at all of these points is pointing parallel, is pointing normal to this surface, is pointing in the right direction, and the electric field, all of these vectors are the same length. The magnitude is the same at any plane that is parallel to this plane. Yes? Right, they are. Okay? So now what kind of surface can I draw? Could you come up with a suggestion? आप बताओ जी. A cylinder. What kind of cylinder? What's the orientation or disposition of this cylinder? Vertical, horizontal? Vertical cylinder. So if I were to draw a vertical cylinder here, like this, that's not going to work, because the electric field on the right side of this edge of this cylinder is going to be smaller than the electric field here. And the electric field is always pointing in the plus j direction, whereas the unit vectors, here they're pointing in the j direction, here they're pointing in the minus j direction, and in between they're pointing in this plane. They're not pointing in the j direction. So this, we will draw a Gaussian cylinder, but it's not going to be vertical. is going to be horizontal. So what we would like to draw, I hope you can see what I'm drawing here. I would draw a cylinder which of course has two ends. Okay, this is the cylinder that I would like to draw, that pierces through the surface. So one right end is to the right and one end is to the left. And this point is P. This point is Q. And we just suppose that this length is R and this length is also R. So I symmetrically draw a Gaussian cylinder that cuts through the sheet of charge. Now what I do know is that the magnitude of the electric field here is going to be the same as the magnitude of the electric field here, isn't it? Because this point is equidistant from this point. And there is really no difference between being on the right of the sheet or the left of the sheet. The only thing that's going to change is the direction of the electric field. The direction of the electric field here is in the plus J direction, and here it's in the minus J direction. And if I were to draw unit normals, if I were to break this Gaussian cylinder into small patches, now there are three kinds of surfaces that I have here. One is the curved surface, and there are two end caps. So if I look at the end caps, the unit normals on the end caps are pointing parallel to the field here, and they're also pointing parallel to the field here. And what about if I draw a small patch here and I draw a unit normal, what is the relative angle between the electric field at this point? So I take any point on this surface, on this curved surface. The curved surface is always normal to the electric field. Okay? So if I take a dot product on the curved surface, locally it's going to be 0. The only contribution that's going to come here is from the end caps. It's just converse to this situation in which the contributions were actually coming from the curved surface. Here the contributions, the non-zero contributions are coming from the end caps. So I can use Gauss's law once again. Suppose the area of this end cap is capital A. So I will use Gauss's law once again, E dotted with dA over the entire closed surface, and on the right hand cap I have an electric field that is uniform EP. dA, I integrate dA, the angle between these vectors on this cap is 0. So cosine theta is 1. I integrate over the area, I get the area of this end cap, which is A, plus I perform a similar integration on this cap, it's again EPA. Once again, locally the electric field is parallel to the unit normals. So I once again get EPA, and if I compute the local dot products on the curved surface, it's going to be 0. And I add up all zeros, I get 0 again. Plus 0. This equals 2 times the electric field at point P into A. This must equal the charge enclosed times over epsilon naught. What's the charge enclosed by this Gaussian cylinder? G. Sigma into the R. So if I would like to find the area or the charge enclosed, I would look at the shadow of the end caps or this cross section on the sheet. So the only area that's enclosed is this circle, which is of the same size as the end caps. Everything else is outside. So what's the area of this shadow of the end caps? It's again capital A. Because I've drawn the cylinder fortuitously so that it's normal to the infinite sheet. Okay? If I do my cylinder so that it's tilted, then the area enclosed will be different, and then I'll have a real problem calculating the electric field. So I use a Gaussian surface that imitates the symmetry of the problem. Okay? Usko match kar diya. So now what's the charge enclosed, my friend? What's the charge enclosed? Into A. So it's sigma into A. and I divide this by epsilon naught. So what I observe is that the electric field at a distance r, I mean this is EP, okay? I'm just parameterizing this with an r. The distance from the infinite sheet, it's EP, is simply sigma over 2 epsilon naught. This is the magnitude of the electric field. So now what I have here is an infinite charge sheet, and you observe something quite interesting you would like to observe here. What is the surprising facet of this result? What surprises you? It's independent of R. You go further away from this infinite sheet of charge, the electric field doesn't change. It's just a constant. It depends upon the surface charge density. Now, how can that be true? Any ideas? How could that be true? You're moving away from an infinite sheet of charge, the electric field remains constant. How could that be true? Shabash. It's an infinite sheet of charge, so you move further away from something that is infinitely large, it remains infinite. You see it, you continue seeing it in its full glory because it's infinitely large. So this is some omnipotent being, an infinite sheet that is so large that you can't move away from it. Okay, so you move away from the infinite charge, when you get closer to the infinite sheet, it still remains constant, the electric field remains constant. However, by symmetry, you notice that the electric field to the right of this charge sheet is going to be sigma over 2 epsilon naught, and since the electric field is a vector, I would like to put some vectorial notation to it. So if these are the definitions of my axis, this will point in the plus j direction, and the electric field on the other end is going to point in the minus j direction. So another conceptual way of drawing this situation is that if this is the plane of the charge sheet, right? So I'm now looking at the sheet sideways. So this is the infinite sheet, and if I were to draw a graph of the electric field, towards the right the electric field is positive. It's a positive sign here. Here it's negative if I were to respect the directions, and it's constant. So on the positive side it has a constant value which is sigma over 2 epsilon naught, and on the negative side it just flips its direction. So I would like to make this go to negative, the same magnitude but negative. So on the left of this infinite sheet it has the same magnitude here but it's negative. So this amplitude is again sigma over 2 epsilon naught. So now if I were to calculate, now if this is a plot of the electric field, now you observe that the electric field is uniform up to this point, then it flips its direction. It just becomes its inverse. It flips its direction and takes up a new value. So if this were a function, is this a continuous or a discontinuous function? It's a discontinuous function. So the electric field can be discontinuous. Remember this. And what is the amount of discontinuity? If I were to measure the discontinuity, it's just going to be the size of this jump. This jump is sigma over epsilon naught. So I subtract this from this, sigma over 2 epsilon naught minus sigma over 2 epsilon naught, I get sigma over epsilon naught. So the amount of discontinuity is equal to the charge density over epsilon naught. So this is quite a general rule that you should keep in mind. Whenever there is a charge, it results, a sheet of charge, it results in a discontinuity in the electric field. Okay? Now I have more examples, but I would like to move on to these demonstrations. So I just shift my gears a little bit जी, क्योंकि यहाँ पे इलेक्ट्रिक फील्ड है सिग्मा ओवर 2 एप्सिलॉन नॉट, यहाँ पे है माइनस सिग्मा ओवर 2 एप्सिलॉन नॉट. इन दोनों के दरमियान डिफरेंस क्या है? सिग्मा ओवर एप्सिलॉन नॉट. दैट्स द साइज ऑफ द जंप. हाउ मच वुड द इलेक्ट्रिक फील्ड चेंज व्हेन इट गोस फ्रॉम हियर टू हियर? इट्स सिग्मा ओवर एप्सिलॉन नॉट. You add sigma over epsilon naught to this, you get sigma over 2 epsilon naught. Okay, so in the next class I'll talk about more examples, but right now what I would like to do is so we've discussed a line of charge, we've discussed a sheet of charge. Okay, by the way, if I have two infinite sheets of charge, all right, both of them suppose are positively charged, and the charge density here is sigma, the charge density here is also sigma. I would like to plot the electric field. Now what you could do everywhere, what you could do is you just consider this infinite sheet of charge and find electric field to this infinite sheet of charge, and then consider this infinite sheet of charge and then take the vectorial sum of all the electric fields. We apply the principle of superposition. And if you do that, you will observe something quite nice. What's the electric field in between these sheets of charge? It's going to be zero. And what's the electric field here? Sigma over 2 epsilon naught? No, it's going to be sigma over epsilon naught, because the charge density, there's a contribution of sigma from this sheet and a contribution of sigma from this sheet. So in between the electric field is going to be zero. Here the electric field is going to jump, and it's going to jump to sigma over epsilon naught. And here it's going to be negative, and it's going to be minus sigma over epsilon naught. This is just a sum of minus sigma over 2 epsilon naught and minus sigma over 2 epsilon naught. You just consider the electric fields due to each of these sheets separately, and look at the discontinuities. Here the discontinuity is sigma over epsilon naught. So here the charge density is sigma, then it becomes constant, and here there's another discontinuity of sigma over epsilon naught because the charge density on this sheet is sigma. Alright, we have to move on. Sorry. Okay, please. No, it can. A discontinuity means some jump. जरूरी नहीं. Not in this case. मैंने आपको दिखा दिया ना, आपको यहाँ पे प्लस नहीं है. यहाँ पे discontinuity और है. What if I have two infinite sheets of charge? One is positive, the other is negative. This is something you should try on your own. It becomes an infinitely sized capacitor. Now what I would like to talk about is the following. The fields inside conductors. And I will build upon these concepts in the next week as well. Now suppose I have a metal. It's a metallic sphere. It's not hollow, it's a sphere. It's not a shell, it's a sphere. Okay? I place this inside an electric field at some instance of time. Now what's going to happen is that this metal has electrons in it, conduction electrons, which are free to move. If they see an electric field, a force is going to act on the electrons, and that force is going to be minus E over epsilon naught, minus E into epsilon, right? The charge on electron into the electric field. So when a mobile electron sees a field, it experiences a force. And when a mobile electron experiences a force, it's going to accelerate, it's going to move. But when we're dealing with static electricity, electrostatics in other words, there should be no motion of charges. We don't have any current. So at the instant that this metallic sphere is placed inside the electric field, the charges will wiggle, the charges will redistribute themselves in a transient, and all of a sudden they will redistribute themselves in such a way that the electric field inside this sphere goes to zero. So what we would have short after we apply the electric field, on the order of microseconds to nanoseconds perhaps, is that the electric charge will redistribute itself and the electric field lines will fail to penetrate into the interior of this metal. So the electric field lines may now change their orientation so that the points, they look something like this. So this uniform electric field now redistributes such that it points something like this. And I will explain this in more detail later. Now, how is that possible? That is only possible. This was an uncharged sphere. Alright? This was an uncharged sphere, so the total charge on the sphere must still be zero. So this is only possible when the charges inside the sphere redistribute themselves in such a way that the positive charges appear here and the negative charges gather here. Okay? So the charge redistribution takes place because there are mobile electrons, they can move to the right, they will leave a depletion of electrons here, so this will become a positively charged end. So this is charging by induction. And I'll explain this in more detail later, but right now what I would like to mention is that the charges will redistribute and the electric field will change its orientation in such a way that the electric field inside remains zero. Okay, so that there is no force acting on the mobile electrons and charges will cease to flow. So in equilibrium there will be no flow of charge anywhere, it's going to be a static condition. If I draw a Gaussian surface inside this metallic sphere, then electric field zero means that I cannot have any charge inside it. So if I take all of these points and if I ensure that the electric field is zero everywhere, then it, by Gauss's law, it means that I cannot have any charge enclosed inside this volume. So all the charge that may exist on a metal exists on its outer surfaces. Okay, and the electric field inside the metal is zero. So now what I have here are two demonstrations. Well, so the first demonstration, this is quite a classic machine here. This is called a Wim-Schurz machine. Quite a strange name, but it's the name of a fine experimentalist, Wim-Schurz. So he was the inventor of this machine. So what I would like to show here is that charges can be built up by virtue of induction. And the charges can be so large that they can cause a breakdown of the insulation properties of air because they produce an electric voltage, and that electric voltage can be so high, of the order of kilovolts, that it breaks down the insulation properties of air and the current flows through the air, and that is what is called a spark or lightning. So this is a demonstration of micro-lightning in a way, and you can read upon the internet what kind of machine this is and how it works. So it has these plates here. Do we have a laser point? It has these plates here, or these metallic fins. These are the metallic fins here, and they pick up charge. As I rotate this machine, they will pick up a charge. And there are two wheels to this. There's a wheel at the front and a wheel at the back, and they will induce opposite charges on the two wheels, and they will then be collected and stored inside these capacitors. So these are called Leyden jars. They store charge, and the charge buildup can be so high that if I connect these levers, I can form a micro lightning between these spheres. The voltage can be of the order of kilovolts. So this is an example of charging by induction. And these are really difficult experiments to perform. They are moody experiments because we live in humid conditions and it's very difficult to keep the static charge preserved for some period of time. So generally, in order to make things work, and they sometimes don't work, so I will give it a try. I would like to dry up this machine a little bit with hot air. थोड़ा सा कैमरा चेंजेस को मैं यहाँ लेके आना पड़ेगा, ठीक है? Let me turn off the lights for a little bit. Probably you'll be able to see the microlightning. So the huge charges can build up, or huge electrical voltages can actually build up. Oh, sorry. Right, this is all right.
Yes.
So I'm going to bring this into motion. Let me turn off my mic for a little. I hope you can see these sparks. These are really large sparks. नजर आ रही है ना, आप यहाँ भी देख सकते हैं। So now I discharge this. Remember that the breakdown voltage Remember that the breakdown voltage of air is 50 kilovolts per centimeter. So if I had a gap of about 5 centimeters or 4 centimeters, and you could see breakdown of air because of the conduction path between these 2 points, it means that the voltage that was developed was about 200 kilovolts. Now with this meager device, just by induction, you can build up such a large charge that produces a large voltage. Okay? Because Q equals CV, V is large, the C really has to be large. So these are Leyden charge with a very large capacitance. So this is an example of how charge can build up on these conducting objects just due to induction. Now the second demonstration that I have is of this machine. Tape है, ये लगा दो. अब फोकस करो. टेप तो नहीं रहेगा. टेप ना चाहिए. चलो देखते हैं. Can you focus now? थोड़ा सा ऊपर कर सकते हैं उसको ट्राइपॉड को इसके ऊपर लेके. Now what we have here is this is called a Van de Graaff generator. Now this produces a charge on this sphere, on this metallic, it's a hollow sphere by the way, by friction. This produced charge due to induction. Right? That's an example of production of charges due to induction. This excuse me, produces charge on this sphere due to friction, and there is a friction between this belt inside the Van de Graaff generator and there are perspex wheels inside. So there's friction between those wheels and the belt that produces a charge, and this results in this surface becoming charged. This surface becomes charged, so because they are connected, they are metals, all of this surface becomes charged. Now what I have here, if you can see on this, we have two small light aluminium spheres, both of them are metal and they are outside the metal. And here, can you focus down a little bit, thoda sa niche lo? Yani ye cheez nazar aaye, haan. And here you also observe two spheres. There are two spheres here, right? And they are inside this metallic hollow can. Now what we would like to do, we would like to build up charge. So this becomes charged, everything becomes charged, and it produces an electric field. We would like to see whether the electric field exists inside this can or not. So here we had an example of a solid sphere. Now we have an example of a hollow can. And we would like to see whether the electric field exists even inside a hollow can or not. And if an electric field does exist, then these aluminium balls will pick up a charge due to induction, and they will be the same charge, so they should repel one another. So if these balls move apart or fly apart, it means that they have picked up a charge, which means that there is an electric field inside this hollow can. So we'll notice the behavior of these metallic spheres as compared to these metallic spheres. Alright? I'm just worried about, because the tape has flaked up a little bit, I'm just worried that moving this is going to make this fall down. But let's try. Okay. So this is a discharging wand. Do you have tape? Then Aliza tape take your place. So this is a discharging wand. It's connected to the earth terminal. So if I touch this device, any charge that's built up will be earth hit. It will go away. The electric fields will disappear. So let me see if this works per se. Okay? I'm going to turn this on. I hope it doesn't fall down. If it does, we'll just try putting some more tape in it. Okay. Ali? ठीक है थोड़ा सा लगा के देख चलो जुड़ेगा दूसरी कॉपर की खुलती है चलो देख ठीक है ना तो मैं पकड़ लूँगा इसको देखने छोड़ दो नहीं ठीक है देखते हैं चलो ठीक है So I started this machine. Right. There's no charge build up, so let me try to heat this up a little bit. There's no charge build up. Okay, let me first try to. इसको भी खाली इसकी सेटिंग ठीक करो तो बार बार ये ना हो। ठीक All right. So now what we observe here is that the two spheres that are outside the metal, they are experiencing an electric field. They see an electric field. So they pick up charge due to induction. And the sign of that charge is the same. So they start repelling one another. However, the two spheres that are inside the metal can do not see an electric field, even though the metal can is hollow. So all the charge that exists on this metal can has to exist on the outer periphery. And inside, Gauss's law is valid. Gauss's law is valid everywhere. So inside, the electric field has to be zero, because in the inner periphery, charge cannot exist. So if you take a Gaussian surface here, the electric flux to that Gaussian surface is zero, which means the electric field has to be zero. These two particular objects do not pick up any charge. They don't see an electric field, which means the electric field inside the interior of this can is zero. Whereas these are seeing a profound electric field, they're picking up charge and they're repelling one another. So what if I remove this electric field by discharging? First of all, you can see sparking here. Again, it's a large charge. Okay, you can hear the crackling sound. बंद हो गई. वापस इन पे ले जाओ. Now what I would like to do, I would like to remove the electric field by discharging this dome. See, when I remove the electric field, the two spheres just fall together. Now I remove this discharging band, the balls are flying apart, I discharge, I remove the electric field, these spheres then cling together. They don't repel one another. So this is an excellent demonstration of Gauss's law, in fact. So these two charged balls are flying profoundly apart. I discharge the wand, the dome, these spheres come back to their original position. Alright, so this is a nice demonstration of Gauss's law that the electric field inside a metal conductor has to be zero. And we have more examples for this on Tuesday, inshallah. And there's going to be a quiz next week. I've also uploaded a homework that is due probably Wednesday next week. Right, thanks a lot.